Welcome to all in the lecture series of functional analysis, and now in this lecture we see the theorem about the algebraic reflexivity. The statement is a finite dimensional vector space is algebraically reflexive. That is the statement. Now to prove this theorem, here we use this lemma. We use this theorem which I write here. Now here to show that a finite dimensional vector space is algebraically reflexive, we start with the finite dimensional vector space. Here we take let capital X be a finite dimensional vector space. As here we start with that capital X be a finite dimensional vector space, then we have to show that it is algebraically reflexive. We show that capital X is algebraically reflexive. To show that it is algebraically reflexive, that is, we have to show that script R of C is equals to X double star, where X double star it is nothing but the second algebraic dual space of X, and here we are taking script R of C, that means the range set of C, where C is nothing but the canonical mapping which is from X to X double star. It is the canonical mapping defined like this: X goes to here, Cx, X goes to Cx, and Cx f, that is equals to gx of f, and that is equals to f of x for all f belongs to x star. In this way we have the canonical mapping C which is from x to x double star, and here script R of C, that is the range set of C, and to show that capital X is algebraically reflexive, that means here we have to show that script R of C equals to x double star. Now to show that script R of C equals to x double star, we use this theorem. This theorem says that let capital X and Y be the vector spaces, capital T which is from script D of T to Y be a linear operator with the domain dt which is contained in X, and the range script R of T which is contained in Y. Then here they are saying then here the first condition says that T inverse exists if and only if Tx equals to 0, implies that X equals to 0. If T inverse exists, then it is linear, and the last condition says that if the dimension of the domain is finite and the inverse exists, then the dimension of the range it is equals to the dimension of dt. Now with the help of this theorem, we prove that script R of C equals to x double star. So here to prove the script R of C equals to x double star, we prove it in following steps. So firstly, we show that the canonical mapping C which is from X to X double star, first of all here we show that is linear. The canonical mapping is linear. This is our first step, and when we show that the canonical mapping is linear, therefore our first condition that the mapping T which is from be a linear operator is satisfied, because here we know that X and X double star both are the vector spaces, and therefore here we show that this canonical mapping is linear, that means this first condition is our satisfied. Now after this first condition, we prove the second condition is that C inverse. Now the C inverse it is from script R of C to X. C inverse exists. To prove this, here we use this statement. To show that here C inverse exists, we have to show that Cx equals to 0 implies that x equals to 0. By proving this, here we get that the mapping C inverse which is from script R of C to X, because here the domain of C is X, that's why we are writing here X. C inverse which is from script R of C to X exists. That is our second step. Now after we show that C inverse exists, then here as we get that C inverse exists, then we are using the third statement. And the third statement says that if the dimension of the domain equals to finite, and here we have to given that X is finite dimensional, that means here we have given that the dimension of the domain, here the domain is X, here the dimension of X, that is equals to n, which is less than infinity, that is given. And in the second step we show that C inverse exists, that means our second condition. And C inverse, here we say that here, and C inverse exists, which we prove in second step. Then by using the third statement, the given condition for the third statement is that dimension of the domain is finite and T inverse exists. So we satisfy here both this condition, that the dimension of the domain, because X is the domain, dimension of X equals to n, that is less than infinity, and C inverse exists. And therefore by using this third condition, here we get that the dimension of range set, that is the script R of C, it is equals to the dimension of the domain. And dimension of the domain, it is, we know that the dimension of X, that is always equals to the, as X is finite dimensional, because of X is finite dimensional, here the dimension of X and dimension of X star both are equal. But again we see that finite dimensional, then its dimension equals to the dimension of its algebraic dual space. As here the dimension of X star, it is of finite dimension, therefore its algebraic dual space, that is nothing but X double star, that is the algebraic dual space of X star. It is also finite dimensional, and its dimension, it is equals to the dimension of X star. In this way we use here that the dimension of X, it is equals to dimension of X double star, and here we get that the dimension of script R of C, that is equals to the dimension of X. And using these two statements, here we are getting that the dimension of script R of C, it is equals to the dimension of X double star, and from this here we get that X double star, it is equals to script R of C. In this way we prove the theorem that the finite dimensional vector space is algebraically reflexive. So let's start the proof of this theorem. So first step, we show that the canonical mapping C, which is from X to X double star, is linear. So we start the proof like this. Let dimension of X equals to n, which is less than infinity, and C from X to X double star be the canonical mapping. Defined as Cx of f, it is equals to Gx of f, that is equals to f of x for all f belongs to X star. In this way we have the canonical mapping. Here we have to show that script R of C, it is equals to X double star. So firstly we show that C, the canonical mapping C, which is from X to X double star, is linear. So we start with any arbitrary two element of capital X. Let X comma Y belongs to capital X and alpha comma beta be any scalars. Then here C of alpha X plus beta Y of F By using this definition, it is equals to, here it is equals to, by using this definition, it is equals to g alpha x plus beta y of f, and it is equals to, now I am writing here, c of alpha x plus beta y of f, it is equals to g alpha x plus beta y of f, and it is equals to f of alpha x plus beta y, and we know that f is a linear functional, and therefore it is equals to alpha f of x plus beta f of y. Now we are writing this f of x equals to alpha gx of f plus beta gy of f, and it is equals to alpha cx of f plus beta cy of f, and it implies that C is linear. The canonical mapping C is linear, and therefore in this way we prove the first step of this theorem, that the C is linear. Now after this we show that the inverse of C exists. Now we show that C inverse, which is from the range set script R of C to X, exists. Now to prove this, here we use the first statement of this theorem, that is, here we have to show that Cx equals to 0 implies that x equals to 0 for any x belongs to capital X. Because here in that theorem, to show that T inverse exists, we have the equivalent statement that T inverse exists if and only if Tx equals to 0 implies that x equals to 0. So here we have to show that Cx equals to 0 implies that x equals to 0. That is we have to show. So we start with any arbitrary element of capital X such that Cx equals to 0. So let's start the proof. Let Cx equals to 0. This implies that Cx of f equals to 0 for all f belongs to x star. This implies that Gx of f equals to 0 for all f belongs to x star, and it implies that Gx of f is nothing but f of x equals to 0 for all f belongs to x star. And here, as f of x equals to 0 for all f belongs to x star implies that x must be equals to 0, as we see in the last lecture, and this implies that x equals to 0. That is, here we start with Cx equals to 0 and we get that x equals to 0, and therefore as Cx equals to 0 implies that x equals to 0, therefore we say that the C inverse, which is from script R of C to X, exists. And in this way we show that the mapping, therefore the mapping C inverse, which is from script R of C to X, exists. This is the second statement. This is the second step of this proof. Firstly, we show that that the canonical mapping C is linear. In the second step, we show that the C inverse, which is from script R of C to X, exists by showing that Cx equals to 0 implies that x equals to 0. Now after this, here we have the second statement of that theorem is that if T inverse exists, then it is linear. By using this theorem, here we get that as a C inverse exists, therefore C inverse must be linear. In this way we get that C inverse exists as well as C inverse is linear. Now after this here, thus we get dimension of x that is equals to n less than infinity and C inverse exists. That is the last statement of this theorem. That statement is that if T inverse exists and dimension of the domain it is equals to n which is less than infinity, then that theorem says that then the dimension of the range, that is the script r of t, it is equals to the dimension of the domain. That is the last statement of that theorem, and we have to use this theorem here. As here dimension of x, that is the dimension of the domain, equals to n which is less than infinity, and we just prove that C inverse exists. Therefore by using this statement, therefore we get that dimension of the range of t, here we have the range of C, the dimension of script r of C, it is equals to the dimension of the domain, and here the domain is x, and therefore here we have therefore dimension of script r of C is equals to the dimension of x. Now here I am giving it the equation number 1. As here dimension of script r of C it is equals to the dimension of x, and it is nothing but it is equals to n. Now the dimension of script r of C equals to the dimension of x, but we know that capital X is finite dimensional. As capital X is finite dimensional, therefore by theorem which we see in the last lecture, if capital X is finite dimensional, then its algebraic dual space, that is the X star, it is also finite dimensional, and also the dimension of its algebraic dual space it is also equals to the dimension of x, and also it is equals to the dimension of x double star, because x double star it is nothing but the algebraic dual space of x star, and x is finite dimensional implies that x star is also finite dimensional, and therefore the dimension of x star that is also equals to the dimension of x double star, and therefore here as x is finite dimensional, therefore the dimension of x star and x double star all are equal. But here from equation 1 and 2 we get dimension of script r of C, it is equals to the dimension of x double star, that we get, and C with the canonical mapping which is from x to x double star. As C with the canonical mapping which is from x to x double star, it implies that the range of C it is always contained in x double star. As this range is contained in x double star, therefore the dimension of script r of C must be less than or equals to the dimension of x double star. It is must be less than or equals to the dimension of x double star. But here if the script r of C it is strictly contained in x double star, that means if script r of C it is strictly contained in x double star, then in this case the dimension of script r of C it is strictly less than the dimension of x double star, because script r of C it is properly contained in x double star, then the dimension of script r of C must be strictly less than the dimension of x double star. But here we get that the dimension of script r of C it is equals to the dimension of x double star. As their dimensions are equal implies that script r of C it is equals to the x double star, because if script r of C it is strictly contained in x double star, then their dimension are not equal. And as here we get that their dimensions are equal, implies that they are equal. That means script r of c it is equals to x double star, and as script r of c it is equals to x double star, we get that the capital X is algebraically reflexive. In this way we show that a finite dimensional vector space is algebraically reflexive.